So, when we met last week, we started looking at um, a different method to determine deflections of different structural types in terms of whether they are beams or they are trusses or frames. We knew from our first few lectures that we could define or we could determine deflections using the geometric methods. But we did explain that the geometric methods are limited in terms of what um, types of structures we can use to determine, like we can use these methods to determine their deflections. So the more versatile method would be the energy methods. All right. And then within the energy methods, there are two main types. We have the unit load method, and then we also have the Castigliano's method. All right. So last week we started looking at the unit load method, or which sometimes we call the virtual work method, and we're able to formulate some sets of equations which can be used um, to determine deflections of various points on a structure. Right. So we first came up with a general equation, which was that for deflections. This is the general equations for deflections or displacements, vertical deflections or translational motion. And also we develop one too for rotational motion, which then would find the slope. All right. So these are the general equations. And then we need to again formulate or reformulate these equations so that we can end up with like specific equations which would work for the different structural types. All right. So we started by looking at trusses, and then we mentioned that for trusses, deformation can occur under three main categories. One is if you have external loads on the trusses. The other can be if the truss is susceptible to temperature changes, like a typical metal-like or steel structures. They tend to respond uh, considerably to temperature changes and also fabrication error. All right, maybe during the welding process or during the bolting process, you could have some errors introduced, which can change the length of the different members of the truss. Okay, so we took the general equation, which is delta is equal to summation of UDL, where the delta here is a real displacement at a point, and then the U has to be the virtual forces in the members, and then the DL has to do with the internal real displacement. All right. So for a truss with external loads or a truss system experiencing external loads, we can derive the equation for finding displacement at a point using this equation right here, where delta is equal to the summation of the um, forces in the members due to a virtual load, and then forces in the members due to a real load, and then times the various length of the members divided by the cross-sectional area of the members and also their respective Young's modulus. Right. Generally, uh, trusses are made up of the same material, right? Hardly you come across trusses that have maybe let's say wood and concrete or wood and steel. They're either typically wood, like what we have in our residential homes where our roof trusses are largely made of wood. Then you also have the steel structure trusses. Again, these are creeping in into our residential facilities, but largely they are used for commercial structures or for buildings that do have large spans. All right. So normally what you would do is that okay, so I'll come back to the external loads points shortly. Um, the other one would be when there's temperature changes. All right. So when there's temperature changes, uh, that can lead to displace, like I mean, different points or different joints on the beams, or sorry, on a truss in this case, experiencing or being displaced. All right, some displacement. So to find that value, we can look at the different temperature, we can look at the temperature changes in the different members, and then use that information to help us to get the displacement at a joint. All right. So that equation has also been given. All right. Great. All right. Then the fabrication error is also can also lead to some displacement. So again, um, the displacement at a joint delta can be determined by knowing the the forces in the members due to the virtual load and also the change in the length, which is really what would occur for any fabrication error. Okay. Going forward, what this means is that we should revise our understanding on how to find forces in members for trusses. All right. There are two uh, methods, even though there are, I think, three or four, but there are two main ones that we all have been taught. That is the method of joints and then the method of sections, right? We use the method of joints when we are trying to find forces in pretty much all the members of the truss, excuse me, or a larger portion of the members of the truss, all right? Then we use the method of sections where you're looking at just a few components or a few members. And so depending on what you are looking out for, one method will be suitable or otherwise. So we went through an example just to look at the various steps involved in trying to um, find the displacement at a particular point, right? So with this example, we're looking at finding displacement, vertical displacement at joint C, all right? So it can be upward vertical or downward vertical. You can initially assume a direction, and then you solve based on that assumption. Okay. So here we assume that C will displace downwards. That's our assumption, even though it could be upwards, right? So pretty much we want to satisfy the equation that we have for the case of external loads, which is in this case, right? So if you look at this truss, there is an external load of 4 kilonewtons acting in the horizontal direction at joint C. I mean, there could be many of these. There could be like 3, 4 loads acting at different joints on the truss. All right. So we take the first scenario, or we try to find the caps N, or the big letter N, and that is the forces in the members due to the real external loads. All right. So that's typically what you do if you had truss in basic structures. So with the loads as they are from the problem, you try to find the forces in the members. All right. So the various caps N. Then when you are done, you take away all external loads, and then you place a virtual load or a unit load in this case in the direction of the display that you want to find. All right. So here so this is for this calculations in this zone is all to find, it's all to find the real forces, axial forces in the members, right? So the real N. Okay. So when you take away the N, then you come in and place a unit load in the direction of the force that you want, right? So you have that. So it's like you're trying to create a new problem or a new structural system to calculate. Okay. So once you place the unit load in the direction of the displacement that we want, you also go through the process of finding forces in the members. All right. But then this will be small letter n because you are looking at what virtual forces or virtual internal forces in this case. So once you find this n, the small letter n, and then you know your big letter n for the different members, you also come and define the length of the members. All right. And it's easier when you tabulate all of this information. Okay. So you create a table depending on which information would be different, right? So here I have in the space, I have the n or the small letter n, which is the forces in the members coming from the unit load, the virtual load I placed. Then we have the caps n coming from the real load. We have the L, which are the length of the members. Here, the area of each member is the same throughout. So I did not bring it as part of the table. If the area of the members are different, you would want to also tabulate that information. Okay. So what do? I multiply small n by big N by L, and I have this information in the tables as well, right? So when I'm done, I sum all of that. So I sum the 10.67 here. I sum the minus 10.41 and then 10.41. So you add them up. Take note, some of them have minuses in front of them. So you sum them up and you get 10.67. But here, this 10.67, it's just only small n, big N, and then L. All right. So this is what you have. But this is not the complete equation. The complete equation also has prefer to make it this way. The summation sign is bigger. All right. So it means that I need to add the area and also add the Young's modulus. The challenge most students face is not really about the tabulation. The tabulation is fine. The challenge students face is the units, how to convert the units so that you work within the same sets of units. And that has been the challenge. But I do believe that it's not much of a challenge if you understand units conversion quite well. All right. So again, I would encourage you guys to brush up on your units conversions, and then that's about it. All right. So the 10.67 in this space here, it's in units of kilonewtons and meters. So it means that your area and your Young's modulus should also be converted into um, kilonewtons and meters. All right. And then once you do that, you end up with a value of 0.113 millimeters. All right. And since our answer is positive, that simply means is that the direction we chose or we assume joint C to displace in is the right direction. So in the beginning, we assume that the displacement would be downwards, and we got a positive value. So that means that our displacement is actually a downward displacement. Okay. So that's what I think we did last week. If we have time at the end of the class, maybe I'll touch on the mid-semester exams. So let's see how far we go. All right. So let's look at some more. Let's look at more examples. All right. Let's look at more examples. So I think I'll just start on a new page or something. Um, Let me see if I could. What am I looking for? This work. That is nice to rule lines. Yeah, let's see how this one works. Okay. Um, Let me pull up an example that will be useful to all of us. So I'll try and solve an example each on the different categories of or different cases of displacements, right? Bear with me for a second, trying to find out if I have some examples somewhere. Mm. Okay, I think that's one nice example. So let's say I have let me see how small. Okay. Okay. Let me just redraw. Okay, so I have this system here. Um, okay, so this is uh, a pretty big system. All right. Okay, so let's name it. So this is A, oops, too thick. So this is A, B, C, D, E. Then there's the F, G, and H. All right. We have support at A and then support at E. All right. Um, so the length here is what? 4 at 3 meters. And then the height um is 4.5, I believe. Yeah, the height is 4.5. If I don't have some information that as I go along, I just update it. All right. So 4 at 3 meters, which will give us a total of 12 meters. And we are to, so this is the question. Determine, uh, see if I can make it work from here. Sometimes you have to be a bit lazy to be smart. Okay. Well, this one will work. Okay. So I'm just gonna just pull in it from somewhere to make my work easier for me today. Um, all right, so we are to determine vertical deflection at joint C due to temperature drop of 8 degrees Celsius in member AB and BC. And also we should determine temperature increase of 30 degrees in member AF, FG, and EH. All right. So here we are not experiencing any external loads, but rather we are experiencing change in temperature. All right. So since it is only change in temperature we are experiencing this time around, it means that the displacement at any joint of interest to us will simply be the summation of forces from the unit load of the members times the coefficient of thermal expansion alpha, and then times the change in temperature of the different members, also times the length of the different members. So if I'm to redraw what I have in this space, let me just copy and paste so that okay, this guy, can I take it off? Okay, it's not allowing me to take it off, so that's fine. Okay, great. So let's look at what we need to put in this data. So joints, so we want to find the deflection at joint C. So our interest is this point, joint C, but it says that there's a temperature drop of 80 degrees in member AB and member BC. So in member AB, there's a drop. Drop means there's a reduction, so negative. In BC, there's also negative 8 degrees. And when you come to member AF, there's an increase of 30 degrees. So it becomes a plus. Then member FG also 30, so plus. There's an increase. Member GH also an increase. So yeah, 4 members with increases. All right. So this is what we have. The other members, there's no change in their temperature. All right. So the first thing that you need to do pretty much is to locate um, the temperature changes. All right. So, all right. So this is important to us. Nothing is going to happen in the space. So once we locate the temperature changes, the next thing will be, so let me just again bring this one up here. Will be to find, we need to find N. All right, where N, this N here, find N, and this N is typically due to the unit load. Okay, so take note, we are finding vertical deflection or vertical displacement at joint C. So I mean that we're expecting joint C to drop or to go up. So I can assume that this is going down, and then at joint C, so at joint C here, I place a 1 kilonewton load. Okay. All right. So what this portion of my work means is that now I have a new truss system with a load of 1 kilonewton. Okay. So with this, I need to find the forces in all the members. All right. So what do we use? We use method of sections. Sorry, use method of joints. You can still use sections, but I mean that you have to use a number of them before you can find out the forces in the members. But joints is usually the better approach. So if you use a method of joints, we need to find the forces in all the members. All right. Because C is at the midpoint, what this implies, you can do that on your own. What this implies is that VA will be 0.5 kilonewtons, and VE would also be 0.5 kilonewtons. Okay, so take a note. So I would HA is 0. All right. Okay. I mean, if you got to do the calculation, so I will only do just like properly do just about I think 2 of the members, and then the rest can easily be done by us. Okay. So for example, if we look at joint A, so joint A, this is joint A. These are our forces in the members. So we need to find since we're looking at, so let's call this small letter N AF. Please don't start. And my screen is messing up. Okay, NAF, the small letter NAB. Okay. Then we have these external forces. So we have VA, then we have HA. We have to find this angle, theta, and we can easily find theta. Okay, so again, this is half. I don't think I put that information over here. So from here to here is 4.5 over 2. Okay, so just take a note of that. And that'll be what 2.25, all right? 2.25. So let's find the angle. What would the angle be? If someone can do that for me, I don't have that information over here. Um, so it's going to be what tan inverse of My opposite is what? 2.25 divided by adjacent of 3 meters. So that gives me an angle of 30. So here theta is equal to 36.87 degrees. All right. So that's fine. Okay. So let's look at which one is easier to do. We can first start by looking at summation of vertical forces equals 0. So this implies that VA plus NAF sine theta equals 0. All right. So NAF will be equal to minus VA over sine theta. Okay. So this becomes our V is 0.5, so minus 0.5 over the sine with the angle of 36.87. So that'll give us minus 0.833. All right. So this will be to find, then we can also find, let me just put the second one over here. If you do summation of forces in the x direction going to 0, what this implies is that then it means that NAF cos theta will be equal to, sorry, not equal to, plus NAB plus HA equals 0. But HA here is already 0, so we take that one out, which means that my NAB or N sub AB is equal to N sub AF minus N. My N looks a bit funny. Minus N sub AF cos theta. So this is just going to be minus into brackets 0.833 cos 36.87. And then this will give us, I think, 0.667. Okay. So we can find the forces in all the members using this format. So you take a joint, and usually when you are selecting joints, you select joints which are easier to solve. Okay. All right. So when we do that, we should end up with these values. So here, I think here is the minus 0.833. Here we'll get, again, minus 0.833. Then, and one thing to take note, I think, let me just write all the values, then I'll let you guys know. So here will be 1. This will be 0.677, and then again 0.677. It's symmetrical because of the position of the virtual load. All right. Okay. So if you can see, I didn't solve for all the members, right? I didn't do this member. I didn't do that member. I didn't do this member. I also didn't solve for this member. All right. And there's a catch to it, or there's a reason to it. When you come to the real object or the real trust, which is experiencing the temperature changes, you would see that these members, member BF, BG, even here, CG, DG, and then DHR, they don't have any temperature changes. All right. And what this simply means is that whatever virtual load or whatever load you get from the whatever force in the members you get from the unit load, you end up multiplying this to 0 because here there's no temperature changes. So 0 degrees, 0 degrees for this guy here, 0 degrees for that. Zero. All right. So these are not experiencing any temperature changes. All right. So let's take a note of that. And even with quite a number of them. So even this guy, the same applies to this. All right. They're not experiencing any temperature changes. And what this simply means is that when you are solving these problems, you don't need to solve at least. It takes practice, but you realize that, okay, if there's no temperature change, then it means that whatever information I'll get from the small letter n will be multiplied by 0 anyways. Okay. We'll see why we are doing that. Okay. And then we also need to find the length of the so this is I. This is I. Sorry, this is I. Okay. So the third case is to find. Yeah, so determine length of the members. Okay. And that's also another fairly straightforward approach. You use your angles, you use your right angle triangle, and then Pythagoras theorems, and then you find the length of the members. So let's look at it. So I have member AB. Let me just draw the lines. So I have member AB. So there's AF, BC. There is FG, GH, EH. Let me change this. This one is CD, DE, and then C. I'm sure I think there's more than what I've written, but it's fine. The key ones are the ones that are in red because they would experience temperature changes. All right. So these are the members. Okay. This is your N. N is in kilonewtons. Then also the temperature change, all right, which is in degrees Celsius. And then you have the length of the members. Okay. So from this calculations here, you'd populate your table with that information. So at joint AB, the force in the member is 0.667. At member AF, the force in that member is minus 0.833. All right. So you can populate your table with that. All right. So here 0.667 minus 0.833. Then again, this is 0.67667, sorry. And then minus 0.833. Normally, your answers are always in three significant figures, right? Yeah. Yeah, this is a minus 0.833. Then again, EH is minus 0.833. All right. So for CD, it is 0.667. Then for DE, 0.667. Then for CG is 1. There are a few more, but they're not too important to us because of the fact that the change in temperature will be 0. So here for AB is minus 8. For AF, we know it's 30 or plus 30. Then minus 8 again for BC. Then it's 30 for these other ones. The rest that we are left with, the change in temperature is 0. All right. So because the change in temperature is 0, it means that if you find the summation, or if you find the product in this case, which is the N delta T times L, at least these guys here the ones on this plane will give you 0. All right. So sometimes you don't, if you have been able to practice this over time, you realize that these values, these ones are not, will not add anything to whatever you are doing. Right. So if you find the length of the different members would also be there. So this will give you 3. You have 3.75, then 3 again, then 3.75, then again 3.75. Okay. So this also be 3, 3, and then 4.5. But you don't need this information because they don't really add up to anything, all right? So for member AB, since we have a drop in the temperature, it means that your N delta T times L will be 0.667 times minus 8 and then times 3. Okay, and this will give you minus 16. Now you do the same for the other members, they give you minus 93.7, then minus 16 again, then minus 93.7, then minus 93.7. Okay, then again, another minus 93.7. Please take note. If you have two negatives multiplying, you get a positive. And if you have a negative and a positive multiplying, definitely is going to be a negative. So please take note of your negatives and your positives. So we find a summation, right? The summation of all of that. And so if you sum everything in a fifth column, that will give you minus 406.8, right? So this 406.8 is summation of n delta t times L give us minus 406.8. All right. But that's not the equation. That's not the complete equation. We know that the displacement, which is I think C, so let me call it CV. All right, is equal to summation of the forces in the members times the thermal coefficient of expansion alpha times delta T times L. So this becomes so we're given that value as well. So this is the coefficient of thermal expansion, which is 1.2 times 10 exponent minus 5. All right. So it becomes 1.2 times 10 exponent minus 5 times negative 406.8. Okay. So if you multiply this, your answer will be minus 0.00488 meters. It is nicer if it's written in millimeters. All right. So here we are getting a negative value. Okay. We initially assumed that our displacement is downwards. All right. But this is a case we got a negative value. What this simply means is that our displacement in reality is actually occurring upwards. All right. So you can maintain your answer this way, is fine. We all know that this answer simply means that it is minus 4.88 this way. Or in some books, or if you want, you can actually go ahead and then convert this to 4.88 millimeters and then show the arrow going upwards. They both are correct. All right, so you can use that approach if you want, great or not. I always tell my students, you know what, leave your answers the way it is in. Once we understand that you had already drawn a free body diagram somewhere, which indicates the directions you assume certain values to be in. Okay. And this is the reason why your free body diagram is always important. Without that, you cannot give context to your information. Okay. Now let's look at the next example. Let's see how we can pull this one off. So let's look at another example. And then here we have another trust system. I'll make some one or two corrections on that. So we have a trust system. Um, and then we have to determine the so it says determine the vertical displacement at joint D. All right. If the member CF, the member CF is 15 millimeters too long, and member EF is 10 millimeters too short. All right. Too long means expansion, too short means what? Contraction. All right. Or reduction. Okay. All right. So here again, we don't have any other form of loading system, or we don't have external loads. We don't have temperature changes. We only have fabrication error. So this is an example of fabrication error only. You can have a combination of them. Let's take a note. All right. So again, step one. I mean, step one and step two can always be interchanged, right? So step one, let's say find. So here, step one, find n. All right. So how do we find n? We um, we take a what's the name? We take a section, and then we take a section, and then we find the so this is what we have. We have our supports right here. So our supports are, let me just redraw this. All right. So we place a unit load, or so just place 1 kilonewton load at D. All right. And since we are looking for vertical deflections, it means that the unit load has to be vertical. It can be upward, it can be downward, right? Not normally by convention, we usually assume downward deflection. That's fine. You can assume upward deflections, okay? So here we've placed a unit load at D, and then we use that information to calculate the N in the various members. All right. Here again, sometimes once you understand how this process works, you'll realize that you don't need to find the forces in all the members. Okay. Again, is there members which will contribute to the overall deflection, I mean, of that particular joint. That matters, right? Um, you see why? So here, um, so usually I prefer to have done step two first, because step two will let me identify which members are actually contributing to the deflection of the joint, right? So here we are told that member CF is 50 millimeters too long. So it means that there has been an increase. So if you take CF, there has been an increase of 50 millimeters in the length of CF. Um, all right. So this is member CF right here. So this member is a critical member because it will contribute to the displacement at D. All right. Then member EF, which is again this member here, sees a reduction of -10. All right. So the other members don't have any change in their length, which means that the change in the length of these other members here would be 0. So this is 0 over here, this is 0 here, and 0, 0, 0, 0, 0. So the only members you are concerned with are members EF and members CF. Okay, so this then would inform you as to which members to find the forces in when you are dealing with the unit load. All right. So again, the critical members will be member EF and then member CF. All right. So in my case, I only saw for the forces in member EF and then member what's the name? Member CF. Right. So again, if I'm to draw my table, I'll focus on just those points. So I look at my members, look at the forces in the virtual system, and then the change in length, and then find the summation of n times the change in length. All right. So for member CF and then the EF, they are the only ones contributing anyway. So the rest, for example, member AB and member BC will not really contribute anything to the system. So these are just extras on the side. All right. So for the N, for CF is -1, for EF is 1, delta L for CF is +15, and then it's -10. Okay. This is in millimeters. Okay. So you multiply the two and you get -15 and then -10. Okay. Please, again, the units are very important. So this one, I'm dealing with kilonewtons and millimeters. Okay. I don't know the values of A, B, and C, B in terms of N, but at least the change in length is 0, 0. All right. So once the change in length is 0, 0, it means that my N times change in length will also be 0, 0. Right. So it doesn't, so those two really do not add anything to my table. Okay. So if I sum this up, I'll get -25. Okay. So we know that displacement adjoint D. So the vertical displacement adjoint D is equal to summation of N times change in length. All right. So this then will be equal to -25 millimeters. Okay. Let me see if there are any questions. I'm supposed to be expecting questions. Let me see. If you have any questions to send to me, you can do that through WhatsApp, or you can text it to the other Lawrence subline, which is not the host, so that I can see the messages. Okay. Oh, okay, I have a few. Let me check what they are. All right, so I'm sorry I didn't see them earlier. I think let me sure that I've not missed any more. Just give me a second. So I have one, two over here. Okay. So I think the same question that I received earlier. So somebody asked that, so going back to, sorry, I have to take you guys all the way back, forgive me. Yeah, so to this point, I think the question that was said, please, for the angle between F and B, angle between F and B, it's difficult to tell what you mean by angle between F and B. So the angle between F and B, do you mean this angle? Is that the angle you are looking at? If you are the one asking that question, you can just confirm with another message to the Lawrence Ablade without uh, the the host attached to it. All right. So with between F and B will be the sine inverse of 2.25. Um, and then over 3. It's difficult to get your question because I don't know which angle, exact angle you are talking about. So you can, so you mean this is my theta. All right. So if this is theta, this angle is 90, this angle is beta. All right. So theta, normally you don't know if you have the length. So let me not make my work messy or Ronaldo. Um, if you have this, okay, this is theta, all right? If you know this length, great. If you know z, you know x, and you know y, whichever set of angles you know, you would end up with the same answer anyways, right? Oh, sorry, which length you know. So if you know only x and y, which is what will happen in most cases, then your theta is simply tan inverse of um, y over x. All right. If you know z and y, then it becomes what tan inverse. So it's so right. Push it up to become tan inverse of y over z. It's not tan, sorry, sine inverse. And also theta can also be cos inverse of x over z. So these are the options, right? Usually we find ourselves using the top most of the time. All right. So you wouldn't because once you use the sine inverse of that will not give you the angle we are looking for, right? Um, so let's check that. Um, all right. Now, how do you get the length values? Again, it's the same process here, the Pythagoras theorem. If you know x and you know y, you can find z, right? Z is what? Z squared is equal to x squared plus y squared. So z is equal to square root of x squared plus y squared, right? If you know the angle too, you can also find z, all right? If you know theta, and you know, for example, if you know theta and you know maybe y, oh, what am I doing? If you know theta and you know y, for example, so you know theta, you know y, you can find z, right? So it means that z will then be equal to, or you can even put it this way, let's say sine theta is equal to y over z, right? So it means that z will be equal to y over sine theta. So you can use this different approaches to find the length of the different members. Okay, so let's go back. All right, so this is where we were. We'll leave it at that. Just to spend 1 hour, no, way less than that, anyways. Um, yeah. So here we got negative 25. Okay. negative 25 millimeters, which is fine. What this simply means is that the direction we chose our displacement to be in should, I mean, in reality, should be the opposite, right? So your delta dV can either be minus 25 millimeters acting downwards, or it can be 25 millimeters acting upwards. That's fine. All right, great. Now let's look at an example, which I wouldn't really solve, but I'll just explain the concept of it. We can try that. And if you have any questions later in the course of the week or weekend, you can get in touch. So let me call it, I'll call it complex, but maybe some extra information should work. Okay. So let's say I have this lines. Um, this is so let me just draw my supports at some point. All right. And I have, so this is A, B, C, D, and maybe E and F. Okay. And let's say the question states that maybe determine display the vertical displacement at C. Okay, so the vertical displacement at C. So it means that we are focusing on this point right here. All right. So if I say determine the vertical displacement at C, um, so let's say that this structure has some external loads. 35 kilonewtons, and then maybe one over here. Let me move this one up a little bit. Okay. Then another load here, which is 10 kilonewtons. Okay, great. And then it says that determine vertical displacement at C. Let's say, oops, let me use black for the truss shown. So you can see that there is a temperature drop of let's say 10 degrees um, for member, let's say BF, draw BF, okay. And a change in length for a change in length of maybe 15 or a decrease. Let me use the word a decrease so that we know what kind of change in length it is. A decrease in length of 15 millimeters for member FC. All right, so this like the trust is experiencing all the three the three categories. All right, so it has external loads. All right, then if you take member BF has a negative drop in the temperature, and also FC also has a drop in or a reduction in the length of the member. Okay, so this problem will simply be a combination of whatever we've been looking at. Okay. So how do we solve this problem? It's fairly straightforward. It's 3 in 1. All right. So it's 3 in 1. So the easiest will be that, okay, Um, the let me put it this way. Okay. So it means that the change in displacement at C, delta CV, will be the one being contributed by the external load plus, I don't know why we draw it this way, plus the one contributed by the change in temperature. All right. Again, by the one contributed by the change in the length. Okay. Now, these three values will be the same. Okay. So this n will be the same regardless of whichever approach you go with. All right. So you can actually rewrite this equation um, in a more civilized, or no, I would say civilized, but in a more in a simple manner where you can factor out the n. All right. You can factor out because the n doesn't need to be solved three times, right? It's the same n throughout, so you can factor out the n. All right, or the small letter, the small caps, small letter, yeah, small letter n, and then you do the same. All right, I would advise strongly. Let's try this. Let's over the weekend. Let's go through it, solve it, and then come and see, and let's see how we can discuss. But it is what we've been doing so far. The three different approaches being combined into one. So sometimes you can have all three, or you can have only one of the three, or you can have two of the three. All right. So these are the options which are available to us in terms of the different loading systems we can experience on the truss to find deflections at a point. Right. All this time we have been finding vertical deflections. It doesn't mean that we cannot find horizontal deflections. We can. All right. So we can take note of that. The major difference will be is that when you are finding horizontal deflections, for example, if the question states that maybe let's say determine, so I'm using the same example up there, determine delta maybe E horizontal. Okay. What it simply means that we place a unit load in the horizontal direction. Okay. So it could be going towards the right, it could be going towards the left. That's entirely up to us which direction we decide it to be in. All right. So these are the key things we need to know with regards to the truss systems or when finding um, whatever I'm looking for when finding displacement for any truss system. Right. These are typically the combinations of the of what we can have. All right. Okay. Now let's look at beams and frames. Right. So we are just continuing with it. Um, if you understand the steps, they are pretty much just like a pattern to it, and then nothing strange occurring. All right. So we over I think since last week we've been saying that the external work done is equal to the internal work done, or it's equal to the strain engine, right? We've explained that anytime you apply some external forces or loads to the system, there's some work being done because definitely there's going to be that rotation or displacement or some deflections, which means that work has to be done, right? From our SHS days, we learned that work is what? Force times distance. If there's no distance, there's no work done. So you can still apply a force, all right, but if there's no movement, of that object, work has not been done, right? So usually when you have a beam or a frame or a truss system, and you apply external load to them, and there's some deflection, it means that work has been done. And these are the external work, right? Before you see evidence of the external work, there should have also been some internal work being done or internal um, energy being stored somewhere or some potential energy being stored. And because this potential energy leads to straining, the rotation we see will cause straining in that elongation or expansion or shear strains or whatever. Shear strains occur through rotations, and then axial strains usually are contractions or expansions. Okay. This stored energy, which is will cause strains, what we define as what strain energy. So the internal work done is a strain energy, right? And then we came up with the other formulation that the um, external virtual work done is also equal to the internal virtual work done. And that's how come we have the unit load, the unit virtual load multiplied by the real external displacement would give us the virtual uh, forces, internal forces times the real internal displacement. All right. So we have this general equation, which is what we have been looking at. So now, how do we convert this general equation into one that is specific for beams and frames? We did something similar for trusses. We'll do the same for the frames as well, and then beams, right? Frames and beams are the same anyways. So let's see what we need to do. Um, okay. So let's say we have a beam. Oops, wrong color. Great. Okay. And let's say we have a point of interest to us. Let's call this point B. Okay. And once we have some loading, some form of arbitrary loading on the beam will undergo some deflections. Right. Now let's say we want to find this deflected or this deflection at B. All right. So what do we do? Okay. Per the unit load method, so let me write, let me put this one here, case one. For the unit load method, we mentioned that if you want to find deflection at a point, we place a unit load at that point. That's like the virtual work method, right? So let's say we place um, a unit load, okay, which is this is from the virtual work approach, okay. So at let's say point B, all right, and it should be um, in the desired direction. All right, so this is always important. Okay, so the direction you want to find that displacement in, it should be in that direction. Okay, so let's say, so I'll just redraw the beam. Okay, then at B, I place a 1 kilonewton load over there. Okay. So that this displacement here, delta B, why the same color? Okay, let me just change it. So this displacement here, delta B, the external work done, in this case, the external virtual work done here will be equal to 1 times delta. Okay, yeah, I'm using B, so it's delta B. All right. And then we know that the external work done should be equal to the internal work done. All right. So for us to understand the internal behavior, we just take a small element of the beam and then try to expand on that. Okay. So let's just take a small element of the beam, an infinitesimal element. Let's call this element, its width is dx, right? So let's say that from, let's say point A to where, I don't want to overcrowd myself. From point A to where the small element starts from, let's call that distance x. It can be anywhere, all right? And then the width of that here is dx, okay? So now let's look at the second case. I'll call that case 2. There's a way to formulate equation for the two of them, right? So we need to also determine, so the first one was to determine the external virtual work. And let's determine um, the internal virtual work in this case. So anytime you apply load, in this case, let's say a punch load to the system, the beam will deflect. All right, so it's going to bend. So if I take this portion that was the x, it means that the x would have undergone some deflection like this. So this is so that I'm just trying to exaggerate um, the x. And then at some point we have the neutral axis where the x remains the same. Okay. And so that's the neutral axis. And definitely, um, so with this differential element or the small element, the x on the beam, for this bending to occur, it means that there are some real moments occurring in the system. All right. And this curvature, this curve usually form a circle, right? If it's to continue, it will form a circle. All right. So we can extend this somewhere here slightly, no, different color. We've gone through this already when we were looking at the beam theory earlier. All right. So the same approach being used. So when we extend this way, we have an angle here. So let's call this angle the theta. So this is the theta, and then we have the x. Okay. And we have already established that the theta is equal to m over ei dx. Right. Where this m here is a real internal moment coming from the real load. Okay. So now let's look at a few things. Let's find the internal work done due to the virtual load. All right. We have also established okay, that for a small system, a change in the virtual load or a change in the virtual work done is equal to um, a virtual internal moment times the theta. Okay, I think that we looked at that at the beginning. All right. So for us to find the total internal virtual work done, then it means that UVI will be equal to MD theta. Okay. Where here the small letter m is the virtual internal moment. But because usually you are integrating over a length and not with respect to rotation, it means that we have to write the theta here in terms of x or distance, all right? So we take this equation and then we place it in, or we replace the theta by that equation. So we end up with UVI being equal to small letter m, big M, over EI dx. So that the dx will be over the span of the what's the name, of whichever member we are looking at. Okay, so I can rewrite this equation here. If I know my limits, let's not equals. If I know my limit of equation, my limit of the integration, which is 0 to L, maybe in most cases, then becomes small m, big M over EI dx. Okay. And we get this virtual internal moment, okay? We get this virtual internal moment by, so we get this by placing a unit load at the point, let me say at the point of interest, or the point that we want to find its deflection. Okay. So that if you go back here, if you go back to this case where we have the 1 kilonewton load, if you take a small portion of that section, the moment in there will be moments, or will be um, small m, all right, which is the moment due to the 1 kilonewton load. Okay, so let's take a look. So that this equation here will be our equation for finding displacement in um, in beams. So this is for finding displacement, okay, in beams, or in beams and frames. Okay. All right. So UVI. All right. So let me complete the equation so that everything makes sense. We know again, we know that what UVI is equal to UVE. So the external and work that is the same as the internal and work done. Let me just reverse their positions rather. Okay. So that 1 times delta will be equal to, so then this then will be what actually we'll use for our computations. All right. So let me move the information here and then rather apply to the one here. Okay. All right. Oops. Let me copy everything. All right. Okay. So this is for displacement in beams. Likewise, we can also find the rotation in beams. All right. So to find the rotation in beams, it means that, so here with this one, we apply a unit load. Okay. In this case, if you want to find slopes or rotations in beams, we have to apply a unit rotation. Okay. which would be what you call a couple. So for the unit load, it's usually 1 kilonewtons. For a unit rotation, it becomes 1 kilonewton meter. Okay. So we apply them at the points that is of interest to us. Please let's take a look. Okay. And mostly when you're applying the couple, we usually choose a clockwise direction for it. That's just by convention. It makes the analysis less tedious. All right. So in that case, I can rewrite this equation here, whereby 1 times theta, where theta is the angle, the slope we want to find, will be equal to 0 to L M, but this is M theta. All right, because this is the moment, the virtual internal moment we will get based on applying a 1 kilonewton meter couple at that point. Okay. Then this is the moment, the big M is the moment due to the real loads, and then divided by the X. Okay. So this is to find rotations. Okay. Whilst this one finds displacement. So here, the challenge with beams is that the two moments, the big M and small m, you need to write them in terms of X, right? Because you are integrating with respect to X. So the moment needs to be developed in terms of X. So let's see an example. Then maybe everything will come full circle to us. Let's say we have a beam. We always use the simplest to explain, which is the cantilever. Okay. And this has some loads. Let's say maybe 12 kilonewtons per meter, for example. The length is maybe 10 meters. Okay. And let's say we find, okay, let me label this. So this is A and this is B. Okay. So let's say find vertical displacement at B, at point B. All right. We know that generally from the moment area method, that's for a cantilever, the displacement at that point is what? PL cube over 3 EI, I believe, right? Something like that. Am I correct? I think so. Yeah. That's just by the way, it's not information that is too critical to us, but at least we might make use of it going forward. Um, so this is supposed to be the displacement. Okay. What just happened to my screen? Oh, the color changes at someone is asking where is Felix? I don't know where Felix is. I should I be asking you guys where Felix is if it's not in. Okay. So now let's look at what to do. Okay. So we have come to this equation here that to find the vertical displacement at any point, this is what we have. Okay. So let's find, so we need to find small letter m and big letter m. The small letter m is so this is for the virtual. Okay, and this for the real. Let's take a look. So you find all these m's in terms of x. Okay. And let's start with the big M. Okay. So with the big M, let me just redraw my structure again. I have my UDL on it. Okay. So if this is point B, my X starts from this section, from B towards A. It's easier that way. So let me cut a section anywhere here. All right. And then deal with the right-hand side. So I'm dealing with the right-hand side. So I redraw this portion. Okay. So this is my B. So let's say, I don't know what M is. So let me show this M, an unknown M. This distance here is X. You have all of these, you have all of that, but they're not too important to me right now. I'm looking at what M is. All right. So this is 12 kilonewtons per meter. So it means that my M, my big M, um, so M is what? Clockwise. If you take moment about X, so let me call this point, okay, let me call this point K, okay? So summation of moment about K will be equal to 0. So this will give me M plus 12 times X over 2 equals 0. So M, I have to always make sure that my big M and my small m are different. So big M here plus 12x squared over 2, which is the same as 6x squared anyway. So it becomes 6x squared equals 0. This implies that my M, big M, is equal to minus 6x squared. So I've gotten the first M. Great. All right. Now let's find, so here, all of these here is to find big M. Okay. So now let's find small m. Okay. So with that, since it's a virtual system that we are looking at, we take out the external load and then we place a unit load at the point that we want to find the deflection, in this case, point B. If you want to find the deflection at, let's say, mid-span of the cantilever, then we have to place the 1 unit load at that span or at that point, please. Where you find your deflection or, yeah, deflection, you place a unit load. Where you find your slope, you place a couple or a unit moment. So again, my X starts in this direction. I cut a section somewhere here. So I would have a beam looking like this. Okay. Again, I want to find small m. So I have a 1 kilonewton load. This distance here is X. So let me call this point K. Okay, I'm just calling this point K. So what this means is that summation of moment at K equals 0. So this would imply that small m plus 1 times X equals 0. Okay. So this implies that what my small m is equal to minus X. Okay. So I have these two equations here. Big M for the real load and then small m for the virtual load. All right. So again, and there's a reason I've been employing you guys to um, Daniel, have I answered you? I'm hoping I have at some point. All right. Yeah. So this is the reason I've been pushing you guys to learn how to write equations of moment in terms of X from the word go when we're looking at how to draw shear force and moment diagram. That if you're able to develop this ability to be able to easily write equations, it will go a long way to help us. And one of the ways it's going to help us is now. Okay. So I have, so it means that my 1 times delta, so in this case is delta at B is 0 to L, where L is what, 10 meters. So just 0 to 10, small m, big M over EI dx. Okay. So this is going to be what? Small m is minus x, big M is minus 6x squared. Okay, dx. So this again will be equal to, this will become 6x cubed dx. So this becomes your integration. All right. Sorry, that's over EI everywhere. Okay. So this means that my 1 times delta B will be equal to, I can bring this guy out here. Then I'll just get 6s cubed over, not over, I mean, I don't need the over anymore. Okay, dx. So if we integrate, we get what? 6x exponent 4 over 4 with the limits being 0 and 10. Okay. So if you put in that value, it becomes 1 over EI into bracket 6 times 10 exponent 4 over 4. Right, because the other one will give us 0 anyways. Okay. Do I have the values of EI somewhere? I didn't put it there. Okay. So let me put in EI. So E is 200 GPa. Okay. And then the I here is 500 times 10 exponent 6 millimeter for gray. Okay. So I can come in here and then say that, okay, 1 times delta B is delta B. All right. So don't worry. So I'm just bringing the 1 so that we always see that there is a virtual unit load that's multiplying the displacement. But usually when it goes to divide, it makes everything easier for us. Or 1 times delta B is always delta B. All right. So here, delta B will be equal to, you can do the math. I'll leave the math out to you guys. All right. So 1 times delta B will be equal to 0.15 kilonewton meter. All right. So this one goes to divide because 1 is in kilonewtons, right? So this one here is in kilonewtons. So it goes to divide, and that will give me delta B being equal to 0.15 meters, which is the same as 150 millimeters. Okay. So what this means is that uh, B will displace vertically by 150 millimeters. Okay. Let's look at another example. Okay. So I'll just focus on more examples. We'll solve like a more complex one going forward. So let's say we have, and again, another cantilever. Okay. And it has this external load, 3 kilonewtons, acting at, let's call that point A. Let's call this point in the middle B. Let's call this point C. Okay. So 5 meters each. And it says we are to determine the slope at B. Okay, so here our E is 200 GPa. Our I is let's say 60 times 10 exponent 6 mm4. All right. So we need to find theta B, which we don't know. But we know that one couple or one kilonewton meter moment times theta B will give us 0 to L, small letter m naught or m theta, sorry, big M over EI dx. So we need to find small m theta and then find big M as well. All right, so that's what we need to do. So what do we do? So let's start with the real loads. All right, and please take notes. All right, the equations that we wrote earlier, which was this equations here. All right. Anytime you write an equation, the equation needs to be valid for a certain span, right? Luckily for us, for the first question, the equation was valid for the entire length of the beam. So it made things easier for us. All right. In some cases, equations can only be valid for certain spans or certain regions. So take note of that. I think I had already mentioned that when we were looking at which methods? Then when we were looking at the integration method also. All right. Okay. So let's since we are finding slope at B, it means that to find small m theta, we need to place a moment at B, which is a 1 kilonewton moment. Okay. So you take your structure that you have, of course, because we are finding the virtual moment, and then we place we place a 1 kilonewton moment at B. So this becomes what? A point moment. I think I mentioned this a few times already. So this becomes a point moment. And then we solve the beam as though it had a point moment. All right. So what do we do? So we have A, B, and C. All right. Because of the position of the point moment, which is acting at B, it means that the equations that will develop will have to develop more than one equation, for example, right? So we have to look at span AB, find maybe let's call this one X1, and then find span BC, also find X2. Okay. So we are moving this way for X. All right. X1 and X2 are under X, all right? It's easier to move from the points where you can write equations easily than to move from the other point, all right? So here, let's take a section through a section through AB. So let's call this section KK. So if we take a section through AB, so let me draw that small section here. So this is what we have up to KK. And then we want to find this moment, small m naught. Maybe let's say m naught 1. Okay, or m theta 1. Okay. In this case, if you're summing moments, it means that your m theta 1 is 0 because there's no any other loading system on it. Okay. Now, if you cut a section through here, let's call that section SS or maybe YY. Okay, SS is fine. So it means that from the left, I will have all of this. Okay. And I want to find, so this is my 1 kilonewton load. And I want to find this moment, M theta 2. All right. And my X2 starts from here. All right. There are different ways to write to do all of this, but this is one of the methods. All right. Okay. So let's all right. So let's see. So you are late for my class, but I have to lose what 20 minutes. So M theta 2. How do we find that? Again, we write equations for it. So let's do that. So here, let's some moments about SS. So these are uh, SS point, the point we cut right here. So it means that M theta 2 minus 1 equals 0. This one we are summing moments, which means that my M theta 2, small m theta 2 is equal to 1. Okay. And here, so this is for span. Let me just say next. So this is for span AB, and this is for span BC. So let's take note of that. Okay. So span AB and span BC. All right. So far we've done for the virtual moment. Now let's look at the real moment. So with the real moment, we take our structure as it is. All right. With a it has a 3 kilonewton load. Okay. So because we're looking at it at different spans, all right. So again, we take a section through here. We call this one KK. Then another one through here, we call it SS. Okay. So again, we have our X1 starting here and our X2 starting over here. So if you look at section KK, this is what we have. A 3 kilonewton load. And we want to find this moment here, the big M1. Okay. This distance here is X. Yes, or let's say X1. We don't know what X1 is. Would later formulate equations on that. Okay. So this will give us what? We have M1 plus 3 times X equals 0. Okay, which means that our M1 here is equal to minus 3X, so S1. Okay. Now, if you look at the second part, which will be cutting a section at SS. So this one is section KK, and this is section SS. Again, we want to find, let's call this big M, M2, and then we want to, so this is 3 kilonewtons. So this is A, and then B is somewhere here. We're not yet at C. This is also A. So it means that this distance here is 5. That much we know. This distance here is our x2, which we don't know, right? Or x2 can vary. Okay. So it means that my M2 will be equal to, or M2 plus 3 times 5 plus x2 equals 0. Right? So it means that my M2, big M2 will be equal to minus 3 into bracket 5 plus x2. So even though it's for one, um, even though it's for what's the name? It's for the same span. We have different, or even though it's for the same beam, there are different spans we need to look at. Okay. So the equation here will be 1 dot theta being equal to 0 to 5. So we have m theta 1 times big M1 over AI dx plus x2 will also start from 0 to 5. So it becomes m small m theta 2 plus big M2 dx over EI. All right. So here we just place in the equations that we've written. Okay, and then we do our integration. Okay. So 1 dot theta, here we are finding theta b. All right. So then this will be equal to limit of 0 to 5. Our small m theta 1 was 0. Okay. So let's take a note, which means that this becomes 0. Then our big M1 was minus 3x. So this is a, yeah, we can decide to, I mean, we can find any of them first. The reason I did the small m first was because through experience, I know that because of where I want to find my slope, it means that my moment equations would vary for the different length or for the different sections. All right. So I won't have one moment equation that fits everything. Okay. Or let me put it this way. Sometimes when you are solving these problems, you could have, let's say, one moment equation, let's say for the real beam, which works for the entire length of the beam. But you might have moment equations for the virtual beam, which will be different for different spans. So if that is the case, then it means that you have to go back and then write additional equations for the moment for the real beam so that you can have those separate spans to deal with. Okay, so that's the general idea. So this is over EI dx. M theta 2 is 1, and then big M2 is minus 3, 5 plus x2. All right, so let me just do it this way. So dx. So dx1, dx2. Then we can just put dx2, dx1 over here. This whole system here goes to 0 because one of the terms is 0, so it's 0. So you only have the right side to deal with. Okay. So 1 times theta b will be equal to, so let me just expand the right side a little bit. So this will be, I can bring the 1 over EI out since it's constant. And I'll have minus 15 plus, oh no, minus 15 minus 3x squared dx2. So dx2, sorry, not squared. All right. So here, if I'm to do my integration, I get 1 over EI. Here I have minus 15 x2 minus 3x2 squared over 2, and then the limits are 0 to 5. Okay. So here you can do that, and then you realize that 1 times theta b will be equal to 112.5 over AI. And then we know what AI is, so it means that our theta b will be equal to minus 0.00938 radians. Our theta b here will be equal to minus 9.38 times 10 exponent minus 3 radians. So that's pretty much it. All right. So this becomes your answer. Let's look at a third example. I wish we can take a break, but we didn't start early and we're a little bit behind. Um, there's one full topic to look at. I was hoping we could start a bit of it today, but I'm told your prof wants you guys exactly at 1 p.m. you're in the classroom. So I get to lose almost about 30 minutes of my time. So let's look at another example quickly. So I think these examples should already be posted on the V campus, I believe. Yeah, so I'm just going to go through them, but I have them already on the V campus. Okay. So let's look at a beam experiencing these external loads. This is 120 kilonewton meter. And then there's a point load somewhere here, which is 30 kilonewtons. All right. Then we have all of these different length. Here's 3 meters, 3 meters, and this is 4.5 meters. Right. So point A, B, C, and D. And then the question says determine delta D. So delta D. All right. What do we do? Right. The simplest thing to note is that because one of the load at B and also the support at C, it means that because of these positions, the points load and then the support at C, if you want to derive equations for moments, the equations can only be valid for a certain span, right? So we can have, so if you take, for example, span AB, we have span BC and span CD, right? We need to find the moment. So the big M for that span AB, find another moment for span BC, find a moment for span CD. All right. So this will be due to the real loads. Okay, so as we have it, then you also come and formulate equations for the small m for the different spans. Okay, and this will be due to the unit load. Okay, since we're looking at deflections, we put a unit load over there. Okay. So once you're able to understand that the moment equations are valid for the different spans, it doesn't matter which one of them you start with first. All right. So you can find the big M, which is due to the real loads first, and then find a small m later. You can do that. Okay. So let's look at it quickly. So let's look at the big M. I'll do part of it, and then you guys can continue with the rest, all right? And then get back to me on it. Because I still want to talk about the mid-sem before we, we depart from here. Um, so this is what we have, and this is so I have my A, my B, C, and D. All right. So you take a section between A and B, a section between B and C, and then a section between C and D. All right. So if you take a section between A and B, then that will help you to find your M1. Okay. The section between B and C will find your M2, and the section between C and D will find the M3. Okay. We usually assume that these our moments are always causing sagging moments, or the sagging moments, right? So if you look at it, again, this is our 120 kilonewton meter load. You can find reactions. So if you find reactions here, your VA will be equal to minus 5 kilonewtons, and your VC will be equal to, I think, 35 kilonewtons. You can always do that. So now let's look at M1. So with M1, we take a section between A and B. So let's find M1. So for M1, we just go this way, take that section here. This is your VA. There's a point moment here of 120 kilonewton meter, and you want to find M1. All right. So this distance here, let's call this distance X1. Okay. So here's X1, which means that to write an equation, let me just take this guy away here. So it doesn't confuse us. So we get M1 minus 120 minus minus VA times X1 equals 0. Okay. Again, look at directions of the moment. So it becomes M1 minus 120 minus, into brackets, VA is minus 5 times X1 equals 0. All right. So if you do all the calculations nicely, you see that you end up with 120 minus 5x1, sorry. Okay, so this becomes my first moment, the main moment, M1. Now let's find M2. To find M2, we take a section between B and C. So we have this long beam. Here's your A, this is your B, and this distance here, let me call this one X2. I have all of these 120 kilonewton moments. This distance here is 3 meters. Okay. So we want to find M2. There's also a VA over here. So again, M2 will be equal to, let me write the equation first. So M2 minus 120 minus, into bracket, minus 5, which is the VA, times 3 plus X2. Sorry, I forgot about the 30. There's a 30 kilonewton load over here. So plus blue, sorry. So plus 30 times X2 equals 0. So here our M2 will be equal to 105 minus, I think, 35 X2. Okay. Now we have to find M3. So the same idea is being used to find M3. So M3, we can withdraw the Fibonacci diagram. We have here A, B, let me just, B, and then C. So so we need to find our M3. This is your X3. We know what this is 3 meters. This is also 3 meters. We have a 120 kilonewton point moment. At B, there's a 330 kilonewton load. Then also there's a VA, and then also a VC. Okay. So to find M3 will be equal to or M3, let me just write the equation. M3 minus again 120 minus to bracket minus 5, bracket open, 6 plus X3. Am I correct? Yeah. Plus 30 times 3 plus X3, then minus 35 times X3 equals 0. All right. And if you sum everything up, your M3 here will be 0. So now we have the three moments from the real loads. We apply the same approach. Um, let's look at the small m's. So let me put here maybe the virtual moments. So again, we do something very similar. We take a cross section of it, and then what's wrong with my screen? Just give me a second. Okay. All right, so this is what we have. So we need to find these small moments, M1, M2, and M3. All right. And so what do? We place, since we are looking for delta D, we place a unit load at D. So that's the one we see over here. Place a unit load at D, and then use that information to find our support reactions VA and VC. Okay. So let's find small M1. So M1 here will simply be equal to or M1. Again, just take a section between A and B, right, to find your M1. Okay, so M1 will be minus into bracket VA. So let me call this distance here. This will be your X1, this will be your X2, and this will be your X3. So let's take note. So because minus VA times X1 equals 0, so our small letter M1 will be equal to minus 0.75 X1. Okay. Again, our M2 becomes M2 minus VA times 3 plus X2 equals 0. All right. So our M2, small letter M2 here will be equal to minus 2.25 minus 0.75 X2. Now let's find M3. M3 will be equal to, or let me put the equation there. M3 minus VA times, is it 6? Yeah. 6 plus X3, then minus VC times X3 equals 0. Okay. So here, M3 minus, what's our VA? Minus 0.75. So brackets open, 6 plus X3 minus VC, which is what, 1.75. X3 equals 0. So here, my M3 um, will be equal to, if you do the math, it should be equal to X3 minus 4.5. Okay. So you have these three, you have so you have your M1, your M2, then your M3. Okay, so for the virtual moment, then for the real moment, you have your M1, M2, and M3. All right. So then next thing is to formulate equations based on that. I mean, to write the deflection equation where 1 times delta is equal to uh, small m, big M over EI dx. Okay. So this is going to be equal to, so let's start with the first span. It's from A to B. So this is from A to B. Okay, take note. So that would give us the small moment is minus 0.75 x1. So minus 0.75 x1. Then the big M, which is the M1, would be 120 minus 5x1. So 120 minus 5x1 all over EI dx. Okay. Then plus the second term, which is between B and C, is also 0 to 3. All right. So again, your M1 is brackets minus 2.25 minus 0.75x. All right. Times, times its corresponding big M2, and that is 150 minus 30, 105 minus, is it 5 of 35? Let me check it before I make the, um, okay, I'm hoping I did the right thing. 120, let me see. 120, so minus 15, minus, plus 15 minus 5. Okay, let me just cross check my values on that side. My M1 is correct, that I know. My M2, my M2 is also correct. Okay. I'm hoping my M2 is correct. It should be. So let me check if I have everything correct. M2 is counterclockwise, so this is different. This is a minus. This is a, also this also here should be minus. Okay, great. Okay, so that gives me what I want. All right, so that's fine. Okay, so I'm still correct. So then this becomes 105 minus 35x over EI dx. Okay. The M30. So because M3 is 0, I mean the big M3 is 0. So because it's 0, it doesn't matter which M we are looking at. I mean, that part of the equation goes to 0 anyways. So we are only left with but let me just add that so that at least it becomes like a reference point to us. It becomes x3 minus 4.5 times 0 over EI dx. So sorry, this is x2, x2, let me just delete. You go, oops. Okay, and here 3, 1. So this guy here goes to 0. Let's take note of it. All right. So we can do our integration at this point. So here's span BC. This is span CD. This is span AB. Okay. So 1 times delta um, D is equal to all of this. Okay. So if we do our integration and we substitute all of our answers in there, you get minus 371.25 over EI for the first term plus 472.5 over EI for the second term. Is it plus or minus? I think it's minus. Okay. Minus, and then this is 0. Okay. So we end up with minus 843.75 over EI. So that if we know what the values of EI, do I have EI here? I think I gave EI, right? So if you know the values of EI, then our displacement at D will then be equal to minus 0.0141 meters, which is the same as 14.1 millimeters, minus 14.1 millimeters. Okay. So this is like a more expansive method to calculate the displacements at a point using the unit load method. The challenge largely would be how to formulate your equations for the moment. That is the major challenge with the beams method, but otherwise the steps are pretty much the same. Okay. Okay. So we have one more topic to discuss, which I think next week should be adequate for it. I would encourage you guys to what's the word? I encourage you guys to revisit your lecture notes in basic structures on the trusses, how to calculate forces in the truss in terms of the axial members, and also revisit your influence line diagrams for beams, right? I learned you guys did that as well, so I wouldn't touch on it. All right. Usually I do, because most cases in first year it's not taught. But since you guys already did that, that is great. It makes the work easier for all of us. So I'd advise you go through your notes before next week. But okay, so let me end the class for now. Let me just end the recording. Then we can talk. All right.